and then you just count. If you go this way, and then this is going to the first triangle. They have the opposite direction. So there must be someone goes up and then will go down, and you let your VI is going to be your first your first vertex, right? And now you consider the path V1 go down to VI. VI go down Vn plus 1, Vn plus 1, and then go down to Vi plus 1, and then continue, go to Vn. Right? And that's a Hamilton path, right? Because you are able to see there's one arc from Vi go to Vn plus 1, and from Vn plus 1 go down to the next one, adjacent one, right? Vi plus 1. And now what you need to do is just add Vn plus 1 between Vi and Vi plus 1. You are able to obtain a Hamiltonian path. So a quick result, what we can obtain is if it's a tournament, right? So if the underlying graph is a complete graph, and then you will always be able to find a Hamiltonian graph from the Digraph, direct graph. Right? So this is, I think, one of the nice results related to the Hamiltonian path. Usually, it's very hard to find a Hamiltonian graph from arbitrary graph, right? And or you are able to show there's no Hamiltonian path. Usually, it's going to be very difficult. Okay, so now let me just discuss one applications of the direct graph. So we are going to look at an old example, right? So which we have considered before. Suppose I have, say, three bottles, and the volume of each bottle are different. So they say this is a 1 liter, and this is a 3 liter, and this is a 4 liter, right? And at the beginning, suppose I have the first bottle is empty, the second bottle is empty, and I have 4 liters in my biggest one. Right? So this is a 4. Let's see, I have 4 liters here. So the question is, can we have 2 liters in the largest bottle and another 2 liters in the medium bottle. So in the 3 little ones, right? After some pouring. Okay, so now the question is after some pouring, right? So I'm allowed to pour this 4 liters into 1 liter, right? So I'm able to get 1 liter here and then 3 liter here. And or I can pour this into 3 liters, and then I'm able to get a 3 liter here and 1 here. Right? So basically is after some pourings, and will you be able to find 2 liters, right, in the largest bottle, and 2 liters in the second largest bottle, right? So is it possible? Okay, so how we are able to attack this problem? Okay, so now what we want to do is set up our model, right? So I have 3 models. Let me assume this is my A, the number of the littles of the wines or waters here. This is B, this is C, right? So what I know is the sum should equal to 4. Okay, so now I'm going to, of course, A is the smallest one, so A is a number from 0, 1. B is the second largest one, so that's a number between 1 to 3, right? And of course, C is, you can solve equation for C. So therefore, what I want to do is I just look at A and B. A is either 0 or 1. B is either 0, 1, 2, 3, right? And C, of course, automatically, basically this is identical to A, B, 4 minus A minus B, right? So this is the smallest one, middle one, and the largest one. Okay, so each status can be represented by a pair of the numbers, and where A is 0, 1, and B is 0, 1, 2, right? So this is the status. And then now let me look at all of the possible status. So you can have 0, 0, right? So that's 0, 0. And then you can have 0, 1. And then you can have 0, 2. So you can have 0, 3. And then you can have 1, 1, 0. 1, 1. 1, 2. 1, 3. You have all of the possible combinations, right? So you are supposed to have A of them. And this is going to be my vertex. So this is going to be all of this is going to be my vertex. And now I'm going to adjoin arcs, right? So into all of this vertex. So there's an arc. Between A1, B1, and A2, B2, if there's a polling to change A1, B1 to A2, B2. So suppose you are able to find a polling, right? So you pull, there's a polling to change the status A1, B1 to A2, B2. And then I'm going to join them up. So basically this says, this is 0, 4, this is 0, 3. And I don't have any arc between them. But I will be, what about this one? So this one is 4. I can pull this into here. So there's an arc here. And if I pull this one bottle into largest one, then I will be able to go back. Right? And then say, for example, from here to here, here to here, there's no arc. And from here to here, you pull 3. You have 3 here, pulls into here, that gets here. And then if you pull this back, you are going back to here. So you are able to obtain another. And so if I go this way, then I give back, and then I'm able to get this one, because I have one little there, right? And let me look at it from, I have one left here, I have 2 here. Does there exist anyone? This is 2. I can call this 2 into here, then I will be able to obtain here. And this is so from this is I have a 3 here. That's I have 1 here. No, there's no way I can do that. Or I can this 3, 1. No, I cannot do that. Goes back, right? So I can do this way, and then it goes down. But anyway, you will see this is after drawing. You will see this is a quite complicated graph, right? So you are able to obtain a graph according to between 2 vertices if there exists a polling to change from one status into another status, and then you join them by a polling, right? By an arc, right? So you can change from one status into another status. And another question is you want at the beginning you want this is the 4 leg, and at the end you want there are 2 littles here, and then you have 2 littles in C. So therefore, this is the original one is 0, right? So you are looking at a path. You are looking at a path from 0, 0. You're looking at a path from 0, 0 go to 0, 2, right? And that's a path. So you can look at a graph and find whether it's possible to find a path from 0, 0 go to 0, 2, right? And also, you can even ask what's the minimal number of points to obtain 2, 2 from 0, 0. 0, 2, 0, 2 to obtain 0, 2 to 0, 0, right? And you can even ask this question. But as long as you are able to draw a graph, draw a direct graph here, and then the answer, look at a graph, and you will be able to find if a path exists, and then you will be able to find compare all of the possible paths. You will find which one is a minimal number, right? So that's kind of a good one example of the application of this direct graph. Okay, so let me give a summary on what we have introduced today. Basically, what we introduce is a parallel result from the graph theory on the undirect graph. Right? So first we have what do we mean? It's a Digraph. So only thing different from the original graph is now on every edge you have a direction. Right? Edge is replaced by arc. You do need a direction. Move out and goes in. And then we have a degree. But now for the degree we have out degree and we have in degree. Because there are some arcs goes in and some arc goes out, right? So this is in and out. And then we have handshake lemma. So you count the number of edge by looking at out degree, or you count the number of edge by looking at the in degree. And then we define again we have a walk, right? And we have trail, and we have a path. So walk there's no restriction. Trail, which means no arc will be repeated, right? So no arc will be repeated. And path basically is no vertices will be repeated. So that's a path. Right? For a closed trail, we call it's Euler circuit, and for closed path, we call it closed trail we call circuit. Closed path we call it's a cycle, right? And then we quickly introduce Euler circuit. Euler circuit. So which means you have to go through every arc on the graph, right? And when it does, when will it exist? So this is Euler theory. On each vertex, the in degree should equal to out degree, right? And 6. And we look at the Hamiltonian path or circle. Hamiltonian path, which means it has to go through all of the vertices. Hamiltonian circle, so which means it is a circle, covers all of the vertices. Right? And for the application, we look at what we call tournament. For a tournament, so which means underlying graph is going to be a complete graph, right? For a tournament, you always exist. You will always be able to find a Hamiltonian graph, a Hamiltonian path. And then last, we discuss a little bit on application of the pouring problem, right? So we have 3 bottles. We have 3 bottles, and of course, you have 3 bottles. You can 3 letters A, B, C, right? But of course, usually, you know, the sum is going to be equal to a quantity, some certain quantity. So therefore, you just need 2 letters, right, to indicate the status of your 3 bottles. And then if you are able to change from one status to another status by one pouring, then you join them by an arc, right? So you see, you can change from here to here. Right? So you can say you can change from here to here, right? So by pulling 1 back into that bottle of 4, and so that you add an arc, right? So you change from here to here, and then you can, if you are able to change from here to here, then you add an arc with direction, right? So now you will be able to, according to all of these vertices, you will able to get a direct graph. And now the question asks, you know, according to the questions, sometimes they're asking you whether there exists a path from one vertex to another vertex, right? So you can translate that into a graph theory problem, right? So that's some applications. Okay, so basically is what I did today is just a review of a few of the concepts from the graph theory, and then add a new concept, which is a direction onto direction of an arc, right? Direction of an edge. So into the graph theory, that becomes a direct graph. Only thing different from the indirect graph is now every edge you do need a direction. That's what we call arc, right? All of the other result basically is almost parallel to what we already obtained. Okay, so basically that's all for today's lecture. Okay.